Well, hello all. Today we're going to be doing stoichiometry. We're going to be doing Kc. We're going to be doing a thing called the rice table. We're going to be playing with equations. We are going to be doing all kinds of difficult and fun things in the physics exam. Hello, Tamika. Nice to see you.
Hello.
Matsadiso.
Hello,
Yay.
sir.
Are you all?
I'm good.
I thought I was going to just talk to myself today, but it's always so much better talking to other people. Myself is a very uncritical audience. I like it when there's someone to point out where I'm being stupid. So your microphones don't squeak. I never get a noise when you join. It's fantastic. But there's someone who's got a microphone that squeaks. Zena. Hello, Zena. Nice to see you.
Afternoon, sir.
Hi. So we got quite a difficult topic today. We're going to be doing Kc now and stoichiometry. Now, just a quick question. Do you guys know about rates of reactions, Kc and a table with start, use up, end, concentration? Just put up your hands if you've kind of heard of it or familiar with it or know something about it. Okay. Tamika, do you know anything about that? Hello, Jade. Nice to see you.
Hi.
So, would it be okay if I just do it like as if you guys know nothing about it, just to go through it for the benefit of, say, people who don't know anything about it? We're doing Kc, stoichiometry, etc. Jade, just do me a favor and just mute your microphone for a second. I just want to hear if yours is the one squeaking. Just see if you can mute. I don't hear any more squeaking. Can you guys hear us squeaking when Jade's microphone is on or not? No. You can't hear us squeaking. Okay, maybe it's just me. Right. Okay, so we're going to be doing this section. Now, tell me, can you see this blackboard or green board? I'm colorblind. Can you guys see it? Okay. Behind me? Is it filling your screen or not? Zena, can you see it?
Yes, sir.
Okay, fantastic. So now we're going to be doing this reaction here. There it is. It's N2O4 gas goes to form reversibly NO2 gas. Okay, so there is our equation. Now it says that this gas is colorless and this gas is brown. Now, do you guys know what is meant by the arrows going both ways? It means this can go to form the brown gas and the brown gas can go to form the colorless gas. So we're going to put it all into a big syringe. Like this. Okay. And we're going to close the syringe. So we say that this is a closed system. Now we've got both gases in there. Okay. So I'm going to throw you guys in at the deep end. I'm just going to go and show you a question paper from 2018. So let me just see if I can share. Okay, here is the question from 2018. It's a question 6 of paper 2. Dinitrogen tetroxide. Do you see it's N2O4? It's called dinitrogen because it's got 2 nitrogens. Tetra means 4 oxides. Decomposes to nitrogen dioxide, NO2. Okay, in a sealed syringe of volume 2 decimeters or 2 liters. So this is what it looks like. The mixture reaches equilibrium at 325 degrees centigrade according to the following balanced equation. Now, the first thing to check is it balanced? Now, let's count it. 2 nitrogens, 2 nitrogens, 4 oxygens, 2 times 2, 4 oxygens. And then it says, when equilibrium is reached, it is observed that the color of the gas in the syringe is brown. Okay, so at equilibrium, the color is brown. So let me ask you, of the 2 gases, which gas is brown? Is it the NO2 or the N2O4? And there you can see that it's got to be this one that is brown. Okay, so that's the one that is brown. Now let's state Le Chatelier's principle. Okay. So who knows what Le Chatelier's principle is? Anyone? Do you know what Le Chatelier's principle is? Okay, I'm going to, Jade and Tamika, you can switch your microphones on, it's fine. So let's give you an idea of what Le Chatelier's principle is. If you've got a balanced reaction like this, and you add something to the left side, it tells you that the reaction, this arrow will increase and it will go to form the brown gas. So if you add dinitrogen tetroxide, you add more when it's at equilibrium, it's going to try and undo what you did. So now it's going to go to the right. On the other hand, if you add some of this brown gas when it's at equilibrium, it's going to go and try and move to the left, and it's going to try and make it into a colorless gas. Likewise, if you change the temperature or the pressure, you can cause the equilibrium to go one way or the other. Now what it just means is, if the equilibrium goes one way or the other, it means at equilibrium, this going to form that is the same rate as that going to form this. But if we add more of this, then it wants to go more to the right, meaning this arrow gets bigger. If we add more of this, it means this arrow gets bigger. And so now this reaction shifts. There's more of this going to the left. I hope that makes some sort of sense. Okay, let's go back to the question. Right, so back to the question. State Le Chatelier's principle. Sure, we've stated it. The syringe is now dipped into a beaker of ice water. After a while, the brown color disappears. Is the forward reaction exothermic or endothermic? Explain using Le Chatelier's principle. Wow. Life is not easy. Okay, so what color did it go when we dipped it in cold water? It said it went colorless.
Mm.
in cold water. Okay? So, which way is the reaction going? Is it going left or right? If it goes colorless. If it goes colorless, is the reaction shifting to the left or to the right?
The
To the left. Okay, great. So now we know that we've done something to move it to the left. And the only thing we did was we took away heat, or we cooled it. Okay, so we took away heat or we cooled it. Okay, so if we cooled it, that means that one heat was either on the left side or on the right side, so that when we removed something, our reaction shifted to replace it. Now, I'm just going to tell you the answer. If we put heat on this side, right? Let's say heat is a reactant. It's needed. And we take it away. Now the reaction will move this way and produce more heat. So if heat was on this side and we took it away, Le Chatelier says the reaction must go to form whatever we took away. I know it's complicated. Just think about it. If it turned color, we know it went to the left because it turned colorless. So heat must be either on the left or on the right. Now let's imagine that heat was on the right. Let's suppose I take away heat. Le Chatelier says we must now replace the heat. So which direction will the reaction go? It will go to the right. And then our reaction will turn brown. But our reaction turned this way, so heat must be a reactant. And then we say that if heat is a reactant, we say delta H is positive. Heat is taken in, plus heat. This plus heat goes to form that. There's the delta H is positive. If heat is given off, we say that delta H is negative. Okay, so that is one way we can influence the Le Chatelier's principle. We can use heat. Okay, so let's go back to presenting. And let's go back to that question just briefly. Okay, so is the forward reaction exothermic or endothermic? It is endothermic. 3 marks. Give a reason. Because heat must be on the left. If we remove it on the left, the reaction moves to the left and it turns colorless, as is explained. Now, 6.3, the volume of the syringe is now decreased while the temperature is kept constant. How will each of the following be affected? Choose from increase, decrease, or remain the same. Okay, the volume of the syringe is now decreased while the temperature is kept constant. How will each of the following be affected? Choose increase, decrease, or remain the same. Okay. Woo! Okay, let me go back to this. I'm going to turn off presenting and go back to that. Now, and here's the next thing that we can do in Le Chatelier's principle. Here's the question you've got to ask yourself. How many moles are there? And how many moles are there? And the answer is 1 goes to form 2. Now, if we decrease the pressure of the cylinder, that means we pull it out. In which direction will it go? Remember, our gas was concentrated. How can we get it to produce more gas? So now we pull this right out, and we've now got a lower pressure. So now we've got to somehow or other get a higher pressure. Remember, pulling out the syringe makes the pressure go lower. So how can we get a higher pressure? Will we get a higher pressure going from 1 mole to 2 or 2 moles to 1? I want you to think about it. The reaction is either going to go right or go left. If it goes from 2 moles of gas to 1 mole, will the pressure increase or decrease? If it goes from 2 moles of gas to 1 mole of gas, what will happen to the pressure? Well, it's going to... Okay, let's just ask you. Who says if you go from 2 moles to 1 mole, it will decrease? Hands up. The pressure. Who says it will increase? Okay, here's how we work it out. A mole of gas occupies 22.4 liters. 2 moles of gas occupies 44.8 liters. So when you go from 2 moles to 1, you go from 44 to 22. But we want more gas to be produced because we already pulled the syringe out, we decreased the pressure. So if we go from 1 mole, which is 22 moles, to 2 moles, we go to 44 moles of gas. So it tells us the reaction is going to the right. You'll have to possibly watch that, but this is the next thing that can influence Kc is pressure. Okay, so let's go again, look at that, at this question. Okay, so let's again at this question. How will each of the following be affected? Choose from increase, decrease, or remain the same. Will the number of moles of N2O4, we're going to the right, okay, to increase the number, the amount of gas. So the number of moles of N2O4 should decrease. What happens to the value of your equilibrium constant? It can never change. The only thing that can change it is temperature. So this one answer must be stays the same. And what happens to the rate of the forward and reverse reactions? Well, the rate of the forward reaction must increase to, it doesn't say anything about the rate of the reverse reaction, but we know that the rate of the forward reaction must increase to produce more of our gas on the right. Okay, so what happens to the rate of the forward reaction? It's going to increase, and I presume the reverse reaction will decrease. Okay, now 6.4. Now we come to the real big difficult question of the day, and it's worth 8 marks. Now, I just want to go back to see you guys. And I'm going to stop presenting. Okay, let's get to our table. Okay, your famous table. I'm teaching a student from another school, and she told me that it's called a rice table. I'd never heard of the name rice table, but when I thought about it, it's a table. I figured it out, and I think this is what she means. You start with a ratio. That's the R. Then you give your initial amount in moles. Then you give your change, which is how much is produced or used up. And then how much you end with in moles. RICE. And then there's another part of the table which is not included in rice, and that is the concentration at the end. Just hands up, how many of you have seen this table before? You've seen it? Okay, seen it? No? Okay, fantastic. This is all new stuff. I love it. Okay, so where do we get our ratio from? Do you see this coefficient here? 1 goes there. 2 goes there. If we had more stuff, we would have more columns in the table. Anyone got a problem with the ratio? It's in a balanced reaction. Okay. Now we need an initial amount. Now, normally, this starts off at 0. You see how I've put a 0 there? Normally, you don't start with any product. You start with a certain amount of reactant. So they've got to give you how much you start with. Then the change is this goes to form that. So some of this, what you start with, is used up, and some of that is produced. So we put how much is used up and produced here. Then we're going to end with a number of moles, and then we're going to use the formula number of moles over volume, or what you ended with over the volume, goes in your last column. Okay, so are there any questions? Happy so far? Right. So let's go and look at that question that they're going to ask. For a full 8 marks. And let's just see if you guys are able to master it. Okay. Here it is, 6.4. Initially, X moles of N2O4 were placed in the syringe of volume 2 decimeters cubed. When equilibrium was reached, it was found that 20% of the N2O4 had decomposed. If the equilibrium constant is that, calculate the value of X. Okay, so let's just read it again. We start with X amount of that. It's placed in a 2 decimeter syringe. When equilibrium is reached, that means at the end, 20% of the reactant was used up, and the value of the equilibrium constant is 0.16. Okay. Now, it would be nice if you had it on a piece of paper, but just have a look at the screen. Okay. So what were we told? We were told we started with X amount of N2O4. Do you see why I've written an X there? Give a thumbs up if you know why we got an X there. Because they told us we started with X amount of that. So our initial amount of X was, our amount of that was X. Who's happy that we started with no product? Our syringe just had X amount. Are you happy with that? We started with no product. Okay, so you're happy with those two. Then they said after a time and at a certain temperature of 300 degrees, 20% of this had gotten used up. 20% of X had been used up. So what does 20% of something mean? It means 20. Per means divided by. Cent means 100. Of means times X. So we're just translating it from English into maths. So 20% of X got changed or used up. That meant how much of X was left at the end. If 20% got used up, how much is left at the end? You see how I knew that if you use up 20%, you've got to be left with 80% times X at the end. Okay, thumbs up if you got it so far. Make sense? Okay. Now, look at that ratio there. The ratio means that if one of that is used, 2 of that is produced. Look, 1 molecule of that produces 2 of that. So if 20% of that is used up, 2 times 20 or 40% of that is produced. Now that is a difficult step. I have to know that if you've got some idea why this ends up as 2 times 20 or 40%. Some idea? Some idea? So whatever that is, double it. Whatever that is, look at those ratios. If that was 3 times, make it 3 times as much. So this was 20 over 100. This is 2 times 20 over 100, which is 40 over 100. So if we produce 40%, how much do we end with? 40%. Do you understand why? If we use 20, we produce 40. If we produce 40, we end with 40. If we produce 40 moles or 40% of a mole or whatever, we end with that. Happy with that? A bit of a thumbs up? You want me to explain it again? Okay, so make sure that the ratios match. Okay, so there's your end number of moles. 80%, 40%. Now, they said it occurred in a 2 decimeter syringe. So now you go to the formula, concentration equals the number of moles over volume. What was the volume? 2. So whatever you ended with, 80 over 100 is 0.8 divided by 2. So now we divide 80 by 100 is 0.8. That goes over 2. 2 times 20 is 40 divided by 100 is 0.4 over 2x. And that's the concentration now. So with that number divided by your decimeters or volume, and then you end up with those 2 numbers. Clear enough so far? Happy with that? Okay. Now we come to the thing called Kc. How do we write the Kc for that reaction? Well, in the case of Kc, we always put product over reactant. Product over reactant at equilibrium, meaning at the end. I mean, here, the concentration. The square bracket means concentration. So now we take, there's your product, 0.4 divided by 2. And we always put that number to the power of. That number in front to the power of the concentration. The concentration to the power of that number. There's a 1. We don't have to worry about it's raised to the power of 1. So now we take that, we put it there, raised to the power of 2. And we take that and we put it there. 0.8 divided by 2 is 0.4, raised to the power of 1. Now we do the maths, that upon that. So when we square this, it's 0.2 squared and x squared. 0.2 squared and x squared over 0.4x. 1x cancels out with 1x. And when I do the maths, I find that x comes to 0.16. Just have a look at that for a while. Does that make some sort of sense? Okay, so we ended up with 0.2 times 0.2 is 0.04 x. We squared the x's, x squared, over 0.4 x. The x's cancelled out, and we left with x divided by x times 0.1. And then to get rid of the 0.1, we divided both sides by 0.1. And so we found x was 0.16 moles, and there's your answer. Quite a lot of marks for that. Every paper 2 has got, as question number 6, this type of problem. Happy? Okay, so I just want to show you something here. I think you can, wait, can you see that? Okay, let's just present our entire screen again, allow. Okay, here is the actual experiment occurring, but they've got this reversed on the other side. It makes no difference. Okay, I'm going to just press play and just watch what happens. Okay, let's just have a look at this one. Watch this. Here is your brown gas. Now I'm going to squash it. Do you see how the molecules combine into a colorless gas? Now I'm going to let it out, and the colorless gas goes into the 2, which is the brown gas. So that's a brown that is brown. When we squash it together, it goes into a colorless gas, which is N2O4. So when it's squashed, it's colorless, and when it's unsquashed, it's brown. Now, are you guys ready to try another question? Okay, do we give last year's paper a go? Okay, let's try last year's paper. Okay, I just want to present again. Present your screen. Let's have a look at last year's paper. Okay, here is last year's paper. Initially 80 grams, 60.8 grams of pure carbon dioxide is reacted with carbon in a sealed container of volume 3. The reaction reaches equilibrium at temperature T according to the following equation. Okay, could I maybe ask you to write it down? Carbon solid plus carbon dioxide gas goes to form 2CO gas. Maybe you could just write carbon solid plus CO2 gas goes to form 2CO gas. Okay, let me go back here. Right. Did you guys manage to copy down C2 solid plus CO2 gas goes to form T2 CO gas? All got it down? Okay. Now, in our rice table, how many columns do you think we're going to need? How many things have we got?
2. Oh, 3.
2, 3. Okay. Now, do you guys know that when you see a solid, you can normally leave it out? We could make do with just the 2 gases, but let's do a column for all 3. Okay. So you're going to have to do this table, write out this table, and let's do a table for all 3. So I'm going to need another column here. Okay. So here is going to be my 1 is to 1 is to 2. 1 is to 1 is to 2 is to 2. Now, here's the first thing that you must ask yourself. Is it balanced? Is it balanced? Let's ask you to count the carbons on both sides and see if they're the same. Okay. Are they balanced? So there's one carbon plus one, two carbons. Two oxygens, two oxygens. So there's two carbons and two oxygens both sides. Balanced. That's the first thing we must make sure, that our reaction is balanced. Okay, now they said we started with 60,8 grams of CO2. Now, ladies, will you be able to convert 60,8 grams of CO2 into moles? Anyone got a formula that we can use?
N is equal to small m over big M.
So N equals small m over big M. Well done. Which is going to be equal to, that would be the mass. Now, who can tell me how I can find big M? Carbon is 12. Oxygen is 16. So what is big M going to be equal to?
44.
So it's going to be 112 plus 16 plus 16, right? And so that is going to come to 60.8 divided by 12 plus 16 plus... Okay, what do you ladies get as your answer?
One comma 382.
1,382. Did you guys get 1,382? Okay. One comma 382. Lovely. Well done. So where are you going to put that 1,382? Which column? In the... Isn't that what we started with? Okay, so we start, and that was CO2. So now we can write here in the number of moles 1,382. All happy with that, so? Now, what did we say? You normally start with how much product?
0.
0. So we can put a big fat 0 there. How many decimeters cubed did this whole thing occur in? Do you remember? Okay, so they told us, let's go back to the problem. Okay, so look at this. At equilibrium, it was found, at the end, it was found that the concentration of carbon dioxide is 0.054. The concentration of carbon dioxide is 0.054, and it says it occurred in 3 decimeters cubed. Okay, 3 decimeter cubed, concentration of 0.054. Okay. So let's stop presenting. Okay. So what is this number here, the volume going to be? What is the volume going to be?
3.
3, exactly, because it was 3 decimeters cubed. And they said that we ended with a concentration of CO2, that's the CO2 column, of 0.054. The concentration was 0.054. Would you ladies known to write it there? This is the only column with concentration in. The last column is the concentration. I think of rice cooked. Okay, C for concentration or cooked. RICE cooked. C, concentration, last column. Now, anyone know how we go from concentration to actual number of moles?
We say the concentration times the volume.
Is the number of moles. Look at this formula. Number of moles cross multiplying is concentration times volume. Okay? Right? So now to go from concentration to volume, we say number of moles equals C times V. There's our concentration, 0.054. There's our volume times 3. So let's just see if we can find a number for that. 3 times 0.054. What do you get?
0.162.
Why do I get a different number? 0.054 times 3. Why do I get 0.162? Who else gets 0.162? Okay. 0.162. Everyone happy with that? Okay. So we started with that. We ended with that. What was the change? We started with that number of moles. We ended with that number of moles of carbon dioxide. What was the change? If you start with that, you end with that. How do you work out the change? Any suggestions?
So the difference,
Sorry?
the difference, you take the
difference.
initial minus the end.
Okay, minus the answer. What do you guys get?
1.22.
Lovely, 1.22. Super. All happy. This is like chemistry Sudoku. When you get good at it, I'm sure you'll enjoy it. Maybe even starting to get a little glimmer of enjoyment so far. Okay. Now, here is the biggest one, the biggest ask of you. Look at the ratio. Your change ratios must always be in the same ratio. So if this is 1, that must be how much is much? Anyone got an idea? These must match each other, but twice. This is 2 times bigger than that. Do you see what I mean?
Mm.
See what I mean? Okay. So how do we get what's going to go in there? So for every one of those used up, 2 of those is formed. So we just say 2 times that. 2 times that is our answer. Some girl, when I was teaching this, showed me an easy way to do fractions. Okay, just watch what she said. This is I like it because you don't require a brain to do this. You just do this. that times that equals that times that. So 2 times that equals 1 times x, and x is your answer. And you will find it's the same thing as multiplying that by 2. So you just cross multiply them. You say that times that, 1 times x equals 2 times that. And so the answer is going to be 2, comma, 4, 4. While we're about it, what is the ratio of this? Now, by how much does this change? Look at the ratios, 1:1. So how many moles of this must we use?
1,22.
Do you see why? 1,22. So that ratio is the same as that ratio, and that must be double. Okay. I include the carbon even though it's not included in Kc, because solids and liquids are left out. But I need it for an answer to a later question. Okay. So if we start with naught, we produce 2.44. How much do we end with?
2.44.
2.44. Now, ladies, how do we go from number of moles to a concentration? Remember, we went backwards there. How do we go from that to that? There's our formula.
Divided by 3.
We say C equals N upon V. There's our number of moles, 2,44 divided by, there's our concentration, 3. So what is the answer going to be?
0,813.
0,813. Lovely. So now we've got that concentration and that concentration. Then they ask us to find the Kc for that. Just let me present and show you. They ask us to find the Kc. So let's see the question. At equilibrium is found the concentration of carbon dioxide is that. Calculate the equilibrium constant, 7 marks. And then find the minimum mass of carbon to be present in the container to obtain equilibrium. 10 marks. Okay, so we've got to calculate a equilibrium constant. So who thinks they know how to write Kc for this equation? What are we going to put on top? Okay. What goes on top? That or that? Always the products go on top. So it's going to be that. CO raised to the power of 2. That CO2 raised to the power of 1. That means we don't have to do anything to it. Happy? And this is in square brackets means a concentration, which means our last column. That's why we needed that last column. Okay, so what's going to go on top now?
0,813 to the power of 2.
813 to the power of 2 over 0,54 just raised to the power of 1. Okay. So now let's work out what that comes to as the Kc. And what do you ladies get?
12.24.
Did you get 0.44 for the total, Casey? What did you get?
12.24.
I get one.
So you said 0.54.
Oh, sorry. There we go. Okay. So what did you get for your final answer?
12.4.
12.24.
12.24. Is that it?
Mm-hmm.
Lovely. That was 7 marks. Did you enjoy that? Did you enjoy that?
It was easy enough, sir.
Okay. And then what is the minimum amount of carbon that was needed to get to equilibrium? How much of the carbon got changed? 1,22 moles of carbon, right?
Hmm.
Do you guys see that? That's why we included it. We used up 1,22 moles of carbon. Now, if 1 mole is 12 grams, what is 1,22 moles of carbon? How will we work it out?
Multiply.
So we're going to say, just see if you can work it out. We could use number of mole. We want to find the mass, right? So we could use that formula. N equals mass over molar mass. We're trying to find M. How many moles was used? We could say 1,22 equals mass over 12. And therefore mass is 1.22 times 12. So mass equals 1,22 times 12. Okay. And what did you get?
14.64.
14,64.
Yeah.
Grams of carbon got used up. 10 marks out of 150. Imagine you do these a few times. How can you ladies begin to see how you can get 100% in chemistry? You're going to get a table like this. You're going to get a balanced equation. You're going to fill in things. The only part you're going to struggle with this is the ratio part. That's used up, that's produced. So those two are used up, those are produced. Plug them in, get your Kc. You can see how if you did a few of these, it's only July, if I'm not mistaken. Imagine by November, and they may even postpone it a bit later. Okay, so there we finished that section. You're going to be brilliant. You're going to be geniuses. If you don't get 80%, I want my money back. So come on, I want to hear from each of you. Anything you did remarkable today, anything that you interested you, anything, and then we're going to go. Okay, you tell me what you did today that made your day. Apart from this. Who's going first? What did you do today that was enjoyable, interesting? I don't believe you had a boring day. Come on. Okay. I went and chopped some wood. I'm busy propping up my trees in the garden. So I went down to the valley there and I took my panga and I chopped trees and I propped the trees up. That was fun. I loved it. I got some exercise, got a sweat. That's what old people enjoy. Okay. Now let's hear what you did that you enjoyed. Come on, you got to think of something you've done today.
So it's not really interesting. But
I'm interested. Yeah.
I was just preparing the meat for dinner because I'm making dinner tonight.
And what kind of meat was it?
It was beef. I'm making beef casserole.
Lovely. Are you doing it in a slow cooker, pressure cooker, pan,
Now in the pot.
in a pot?
Yes.
How many hours you gonna boil? You gonna boil the hell out of it till it's nice and soft?
2 hours. That's why I
Yeah.
did it so early.
Now that's interesting to me. I find that fascinating. Okay, you
Thank
did
you.
Okay, next. Who did something else? And your family's gonna love that. I know that. Okay, next. You're not getting away. Okay, so Zena, what?
So I practiced work energy and power calculations, and I got it right for the first time.
Really, work energy power? You know what? My mind has just gone a blank. What does that involve? Work energy? Oh, those like upslopes and what exactly did you do?
I did like using the like conservative and non-conservative forces and
And that formula. Fantastic. Okay, well that's maybe even beats the casserole. Okay, Tamika, what did you do?
I was helping my daddy clean the yard.
Okay. Or you finish. When you finish, can you come and help me clean mine? Because that's exactly what I'm doing. I'm propping all trees up so that I can walk through my yard. My yard has grown over. Lovely. Okay, well that was great too. And what's diesel?
Not much.
Okay, tell us about that. Not much.
I didn't do anything.
You got up. You're alive. You well. Did you listen to some music? Watch TV? Do something?
Help clean the house.
Cleaning the house. Isn't that wonderful? Did I hear right? You clean the house. Well, let's give you a well done. Your family's also going to love that. Not as fun as cooking a casserole, but it's got to be done. Okay. Again, ladies, thank you so much for coming on. And we'll put this online. And yeah, great stuff.
You,
And then
sir.
we'll probably do something tomorrow. I'll have to think what it was, but I don't think we're going to do more of this because you did two difficult problems from the last 2 years' papers. Fantastic. I don't think you were completely lost, so we'll think of something, probably some physics tomorrow. I think we need a change from chemistry. Okay, cheers then.
Bye, sir.
So
Bye, guys.
bye.